All right, so we're going to look at this example of two random variables involving tossing two coins, okay? And from this, we're going to determine if the two random variables are independent or not. And we're basically going to see their relationship with each other, okay? And we're starting from the ground up. So we're going to define x as the number of heads on the first coin and y as the total number of heads in two tosses. So our sample space is tossing two coins, right? So one of the outcomes could be heads, heads, right? Another outcome could be, let's say, heads, tails. Another outcome could be tails, heads. And the last outcome, we could have tails, tails. So this is our sample space. Now let's go ahead and move on to our joint PDF. So it's going to look something like this. Scoot down a little bit. Okay, so x dash y. Oh, let me fix that a little bit. There we go. And then our x's. So x is defined as the number of heads on the first coin, so that we could have 0 heads on the first coin and we can have 1 head on the first coin. Now y is defined as the total number of heads in two tosses. We can have 0 heads in two tosses. We can have 1 head in two tosses. And we can have 2 heads in two tosses. Now, this right here is the probability that we have 0 heads in the first coin and 0 heads in the two tosses. So as you can see, the outcome TT fits that, and that is 1 out of 4 outcomes. So that's 1/4. Now the probability that the first head, that there isn't a head in the first one, and there is a total of 1 head, right? That is, let's see, this guy here, tails, heads, right? So that's also 1 out of 4. Now, the probability that the first toss has 0 heads and the total number of heads in the two tosses is 2 is not possible, right? The first one would have to be a head in order for there to be a total number of 2 heads in the two tosses. So that's impossible. Now let's look at the first toss being a head and the total number of heads being 0, right? That's also impossible. We can't have 1 head in the first toss and there being 0 total heads, right? Now the next one is the first toss is a head and there's a total of 1 head. So let's see, the first toss is a head and there's a total of 1 head. So that is this outcome HT, so that's 1 out of 4. And now lastly, the first toss being a head and the outcome having 2 heads, right? So that's HH, so that's also 1/4. So here is our joint PDF. And from this, we can come up with our marginal distribution. Okay, so we want to find the probability that x is equal to 0. The way we can do that is we can just add all of these together. So 1/4 plus 1/4, which is 1/2. Next is the probability that x is equal to 1. So that's, again, 1/4 plus 1/4, which is 1/2. All right, next we want to do the probability that y is equal to 0. So now we're going to add this column. So that'll be 1/4 plus 0, which is 1/4. The probability that y is equal to 1 is equal to 1/4 plus 1/4, which is 1/2. And lastly, the probability that y is equal to 2 is that 1/4. So this is our marginal distribution. Now from here, we're going to determine independence. So remember, for independence, we need for every input, right? For every input, we need the probability that x is equal to x, y is equal to y, is equal to the probability that x is equal to x times the probability that y is equal to y. and it has to work for every single one of them. So what I'm going to choose is I'm going to say, okay, well, let's look at the probability that x is equal to 1 and y is equal to 2. So the probability that x is equal to 1, so here, and y is equal to 2, that is 1/4, right? From our joint PDF. Now let's look at the probability that x is equal to 1. As you can see, that is 1/2, right? And the probability that y is equal to 2 is equal to 1/4. So the probability that x is equal to 1 times the probability that y is equal to 2 is equal to 1/2 times 1/4, which is 1/8. And as you can see, the probability that x is equal to 1 and y is equal to 2 definitely does not equal the probability that x is equal to 1 times the probability that y is equal to 2, right? Because this is equal to 1/8 and this is equal to 1/4, so they're not equal. Therefore, this implies that x and y are not independent. They depend on each other, right? Okay. So we're going to showcase this dependence through our correlation coefficient and covariance, right? Because remember, if they're independent, then their covariance is 0, but we're going to show that the covariance is not 0. So next, we're going to look at the expectation of x and y, right? So the expected value of x, remember, is equal to x can take on 0. So 0 times the probability that x is equal to 0 plus 1 times the probability that x is equal to 1. Remember, x could take on 0 and 1. Okay? So this is going to be 0 times the probability that x is equal to 0 was 1/2 plus 1 times the probability that x is equal to 1 is 1/2. So the expected value of x is going to be 1/2. Now let's look at the expected value of y. And that makes sense, right? Remember, x represents the number of heads, right? The number of heads on the first coin. And you would expect that heads would come up half the time, right? So that makes sense. Now let's look at the expected value of y. Okay, so y can take on 0. So 0 times the probability, not x, the probability that y is equal to 0 plus 1 times the probability that y is equal to 1 plus 2 times the probability that y is equal to 2. So this is 0 times the probability that y is equal to 0 is 1/4. Now 1 times the probability that y is equal to 1. Y is equal to 1 is 1/2. Plus 2 times the probability that y is equal to 2. 1/4. All right, so of course that's 0. This will be 1/2. And this will be 2 times a fourth is 1/2. So the expected value of y is 1. All right. So from this, right, let's go ahead and look at covariance. And we already know that the covariance can't be 0. But remember, covariance of x and y is equal to the expected value of x times y minus the expected value of x times the expected value of y. Okay, so of course we have to find the expected value of xy in order to find the covariance. So we have the expected value of xy is equal to, so this will be 0 times 0, probability that x is equal to 0, y is equal to 0, right? Basically, you have to do all of these, right? So the next one would be 0 and 1, and that's 1/4, right? So plus 0 times 1 times the probability that x is equal to 0, y is equal to 1, plus 0 times 2, the probability that x is equal to 0, y is equal to 2. Of course, these are all going to be 0, right? But I want to showcase how it relates with the joint PDF, right? So I did these three, right? 0 times 0 times a fourth, 0 times 1 times a fourth, 0 times 2 times 0, and then we're going to do these, right? Plus 1 times 0 times the probability that x is equal to 1, y is equal to 0, plus 1 times 1, probability x is equal to 1, y is equal to 1. And lastly, 1 times 2, probability that x is equal to 1, y is equal to 2. Okay, so we already know that this one's going to be 0, 0, 0, 0. So realistically, we're only looking at these last two, right? So it's going to be 1 times, now what was the probability that x is equal to 1, y is equal to 1, x is equal to 1? So a fourth plus, and then 1 times 2 is 2, times the probability that x is equal to 1, y is equal to 2, a fourth. So that's a fourth plus a half, so that'll just give us 3/4. Okay, so now the covariance of x and y is equal to the expected value of xy, which we calculated as 3/4, minus the expected value of x times the expected value of y, so a half times 1. So 3/4 minus basically a half is just a fourth. And of course, you can see that the covariance of x and y is not 0, so that showcases that x and y do depend on each other, which we've already established using the definition, right? But we need the covariance in order to showcase the correlation that these have among each other. So in order to do correlation, we also need the variance. So let's go ahead and calculate the variance of each. So remember the variance, let's say, variance, the variance of x, remember, is the expected value of x squared minus the expected value of x squared. So we already have the expected value of x, right? And we can square it, but we need to find the expected value of x squared. So let's go ahead and do that. So the expected value of x squared, remember, x can take on 0, so 0 squared times the probability that x is equal to 0, plus 1 squared times the probability that x is equal to 1. And that's still going to be just 1 times the probability of x is equal to 1. So in this case, the expected value of x is the same as the expected value of x squared, which is 1/2. So it'll be 1 times 1/2, because that's the probability x is equal to 1, and that's 1/2. So the variance of x is just equal to a 1/2 minus, and then remember the expected value of x was 1/2, but we're going to square it. So that's 1/2 minus 1/4, which is 1/4. All right, so now let's go ahead and look at y, right? So we need to find, for the variance of y, it's the same. We need to find the expected value of y squared, which is, that's 0 squared times the probability that y is equal to 0, plus 1 squared times the probability that y is equal to 1, plus 2 squared times the probability that y is equal to 2. Right? So, of course, this is going to be 0. This will be 1 times the probability that y is equal to 1. Let's go to our marginal. Y is equal to 1 is 1/2. Plus 4 times the probability that y is equal to 2. Y is equal to 2 is a fourth. So this will be 1/2 plus, 1/4, not 4, right? So let me get that really quick. Okay. 1/4, which is 1, and 1/2 plus 1 is 3/2. So the variance of y is going to be the expected value of y squared minus the expected value of y squared. The expected value of y squared we just calculated is 3/2 minus, and then the expected value of y, remember, was 1. So this will be 3/2 minus 1, which is 1/2. Okay. Now, the correlation coefficient formula requires us to calculate the standard deviation. So remember the standard deviation. So we know that sigma squared of x is equal to the variance of x. And the variance of x is, we calculated that to be 1/4, right? 1/4. And the variance of y, right, was equal to, we got that to be 1/2, right? Now let's calculate the standard deviation. Okay, so the standard deviation is simple. SD of x is simply this, right? Which is the square root of the variance, right? And remember, the square root of the variance of x is the square root of 1/4. And then the standard deviation of y is equal to this, which is just the square root of the variance, which is the square root of 1/2. Okay. Now, lastly, the correlation coefficient. Okay, so correlation coefficient. Okay, so the correlation coefficient is rho of x and y is equal to the covariance of x and y over the standard deviation of x times the standard deviation of y. Okay, so we have all those goodies. Remember, the covariance was 1/4. Let's go back up here. Remember, the covariance was 1/4, and that's going to be over the standard deviation of x, which is the square root of 1/4, times the square root of the standard deviation of y, which is the square root of 1/2. Now, this is the same thing as a fourth over the square root of 1/4, and 1/2 can be written as 2 times 1/4, right? And you'll see why we do this, because this is the same thing as 1/4, and we have the square root of 1/4 times the square root of 1/4, which is 1/4, and we're left with the square root of 2. And of course, 1/4 over 1/4 is 1, so we have 1 over the square root of 2. We multiply top and bottom by the square root of 2, and that gives us the square root of 2 over 2 for our correlation coefficient, which is approximately 0.707. And remember, the closer it is to 1, the closer it is that they're like an ideal fit, like for sure. Okay, so this illustrates that the random variables x and y depend on each other, and we use methods such as the covariance in order to measure that connectedness.